So we will have to have either spherically symmetric or very far apart so that any density differences don't matter. Right, so that's the criteria for using force. Right, from force, we can divide by mass or divide by mass to get field strength. So we got field strength. We can also talk about gravitational potential energy and potential. Right, and energy to potential, you divide by mass times mass. Right, so if you have gravitational force, when this force does work, there is gravitational potential energy. So gravitational potential energy is given by gmm over r. But the difference between these two is the force is vector, the energy is scalar. Right, so far so good. Okay, field strength and force, potential and energy are quite similar, but they have a per unit mass here. So what's the difference between these two? The top and the bottom.
One is area on the top.
No, I'm talking about the difference between force and energy versus the difference between field and potential.
One is
directly applied on an object and one is for per unit mass of an object.
Okay, so what Iman said, for force and energy, you actually need to directly apply on the object, which means you need the pair. For force, you need two objects. For energy, you need two objects as well. I mean, minimum of two objects. You can have force from multiple objects, and you can have energy from multiple objects. But they can't be they must be caused by another object. So usually what we will say is there's a central mass, and then this mass produces a force on another mass. Of course, according to Newton's third law, the force will also be produced on the central mass. The same is true for the energy. If you have one mass, another mass will have potential energy in lieu of the fact that there's already a mass in the first place. Right? Whereas for field strength and potential, you only need one object in order to produce a gravitational field. Right? So there isn't a second object to compare to. The mass has disappeared here, right? The second mass has disappeared. That's why we divide by mass. Right? But does it make sense, right? I must talk about something, right? So what is the thing that we're talking about in field strength and potential? There's still a thing. It is not a mass, but there's a thing. So, it's not a mass. It's not another mass. This property of field strength and this property of potential is attached to space itself, a point in space, an abstract point in space. So normally we will say, oh, if there's nothing in the universe and nothing affecting anything, you have a vacuum. So that literally is nothing. But you still have points in space. You could still assign a coordinate system and designate this is point X, this is point Y, this is point Z, and so on and so forth, right? So you can still talk about points in space. So these properties, they are points in space. How are they properties? They are properties that are caused by a central mass. So for example, if I have empty space and suddenly I put in a mass. Basically what I'm saying is the mass modifies the property of space. From before, there was no property. Now all points in space have a property of gravitational field strength. And that property being, if I were to put a mass at that particular point, that mass will now experience gravitational force. And in fact, the field strength magnitude will tell me what that force would be depending on what the mass I place at that point. That's why gravitational field strength is the force per unit mass at a point. Right? So this property is attached to points in space. They're not attached to objects themselves. So it's usually independent of the object that I place at the point. So the moment I place an object, I can find the force, but the field strength still remains the same. Right? The same is true about potential. Basically, if I have an empty space, there's no property for space. Right? Every point is just the same as every other point. But the moment I plonk a mass into the space, every other point in the space there now has the property of, if I were to put an object here, the GPE of the object would depend on how much mass there is I put here. Right? So these two apply to pairs of objects. These two apply to points in space. Right? So they're very useful concepts. So this one's tied to the concept of a field. So before we had sci-fi, fields were very hard to imagine, but now we can visualize fields, right? Fields are basically a property of space itself. So now the property is just that if I have a whatever type of object, so for mass, I will have a gravitational field. Then the gravitational field's property is if you put a second mass there, it will experience gravitational force. So you end up having similar things for other kinds of fields. You have electric fields. Electric field says if I have a charge in space, the property of space changes such that if I were to put an object with charge again, it will experience electric force. Right? And magnetism also is the same. If I had a magnetic object, it changes the property of space such that if I were to put another magnet, it will experience a magnetic force. But actually you'll learn in J2 that a magnet is nothing but a moving current, a moving charge, a current. Yeah. So to get magnetic force, the field is if I have a current and I have another current in space, that current will experience a magnetic force. Right? Quite interesting, right? Because currents must be caused by charges. So electric fields and magnetic fields in the end will be related.
Magnetism is moved out from O level this year.
This year.
Yeah, they move out magnetism.
Wow, that's weird because then they'll die in A level because magnetism is definitely in A level.
But it actually killed me in O level.
Electrocuted you in O level.
Actually killed me in O level.
It could have actually killed you in O level unless you came back from the dead like Lazarus. Okay, so okay, we still have one more set of relationships to talk about, right? Where is it? Yeah, the graphs, right? The graphs come from the relationship that's on the left-hand side to the relationships on the right-hand side. So if you find the area under the force distance graph, you will get energy. So let's integrate. Then to get back force from energy, the opposite of integrate is differentiate. But that's quite complicated to most of the H2 students. They like hate math when it comes into physics, right? So instead of telling them integrate and differentiate, we'll tell them, oh, this one is area under the graph, then this one is gradient. But y'all can, right? Y'all love calculus, right? Yeah, calculus. Love calculus. Right? And the relationship, since this is per unit mass, the relationship is preserved. To get gravitational potential from field strength, it is area under the graph, under the field R graph. And to get back the gravitational field strength at a point in a gravitational field, if you know the potential, then it is differentiate with respect to R. Right? That explains the area under the graph area thing. But what concept explains area under the graph in the first place? So that was one of the most asked questions after lecture 3. They're like, hey, but why is it area under the graph?
Something like impulse.
Potential energy
It's not
is
impulse.
the integral of force.
Yeah, but why? That's literally the relationship. But why is the relationship? Why does the relationship exist?
Force times
Energy is derived. Energy is derived from the force exertion of an object.
And
So the potential to do some energy is the potential to do work. So since potential is the energy is the potential to do work.
and what's work?
So work is force times.
Yeah, impulse.
Work is?
F3.
It's not impulse.
Momentum.
It is the work energy theorem.
Yeah, can I get one more for that?
The work energy theorem tells you that the increase in kinetic energy is related to the work done, and the work done is force times distance. So this relationship you all learned in secondary school, which we did in earlier topic, this is for constant force, right?
Good afternoon. Agenda reminder to your second temperature. Thank you.
Maybe at 2 o'clock.
Yeah, I have
Everybody feeling okay? Anybody family member suddenly sick? Really?
sick of my shit lah.
Okay. Not yours lah, maybe. Okay, so this is constant force. Then if you multiply the distance moved by the constant force, you get work done. Right? However, you have also done this before, right, in syllabus. Do you remember what graph this is? Elastic. It's for the stretching of an object, right? And in this case, we didn't have a constant force. So the work done becomes the area under the triangle. So normally this is area under the rectangle, this is area under the triangle. Now our force is just going to be an inverse square force. So it's a force that looks like this. Right? Inverse square. So it's just area under the inverse square graph, which is why instead of just calling this some funny shape, what would you call this shape?
Curve. Area under curve.
slope area shape. We just say area under the curve, which is literally integration, right? So that's where the integration comes in. So to some students, they'll look at this relationship, they'll be like, the teacher say energy is integral of force and R, so I'll just memorize it. Then I ask them why, then they don't know, right? But the real reason is the potential energy is basically the work done by the gravitational force, right? So therefore, the force times the distance moved will give you the energy. That makes sense, right? It's just that the force keeps changing. So I can't just do a simple multiplication. I need to do the integration. So that's how all these relationships come together. Any questions about any of these quantities, concepts?
Miss J, what is your energy on negative value?
Good. So that's the next question that I want to ask you, okay? So if that's the case, right, you'll notice that in this expression, something is special about them, other than the fact that inverse square law and inverse R law. In force, there's a negative sign. What does it mean?
Negative direction.
It's a what?
Negative.
It's a what? Attractive force. Negative direction. So direction must be defined, right? So basically in gravity, what was not really very obvious was our coordinate system is no longer a XY Cartesian coordinate system. Our coordinate system is what we call spherical coordinates. And I think I touched on a little bit of that in circular motion, right? I said that normally you have your XYZ Cartesian coordinates. In spherical coordinate, you have an origin, and in your origin, you have radius.
Polar.
Yeah, so it's polar. Polar is a type of it. So, if you have an object, this direction is the radius. It's a positive vector that extends to infinity. But the other direction is also the radius. It is also extends to infinity. So in order to differentiate between these two radius, I will start from an arbitrary direction and measure the azimuthal angle. Right? So depending on this angle, I can specify which particular radius it is. Given that the radius is 5 meters, I can specify if the radius is here, that point there, or the point here. I will define one direction as my arbitrary direction and measure phi from there. Right? Then I still haven't specified a point in 3D space, right? Currently I've specified only a point in a plane. So in order to make the coordinate known, the 3D space, how high and how low it is, normally we use the z-axis in Cartesian coordinates. So here we will use the altitude angle, this angle. So this one is 180 degrees maximum. So phi is 360 degrees, theta is 180 degrees. So our coordinate basis becomes x, y, z normally changed into r, phi, theta. So this is actually a little bit complicated, but it's important if you want to do calculus for vectors later on in university. Yeah, so this is basically a coordinate system. So in the coordinate system, right, you have an origin, and the radius direction is the only one that you need for gravitation. You're pointing outwards. So to point back at the origin, which is what Iman said, an attractive force, okay, implies that you are opposing the sign convention. So that's why the force, right, these numbers are always positive numbers, because the radius is always positive in the radial direction, right? Then the masses are always positive, and this is a positive constant. So in order to get your attractive force, it is negative. Okay? For electric charges, right, you can have repulsion and attraction. So the charges can become opposite signs so that the force can become positive, which is repulsive, or negative, which is attractive also. So that's the origin of the negative sign for force and force per unit mass at a point. So that has to do with the coordinate system and the fact that it's a vector. The reason why energy has a negative sign is completely different. It is not because of vector, because energy is not a vector, right? Energy you can only either gain or lose. So for energy it is negative because, number one, at infinity, your U equals to 0. You have no energy at infinity. You are defined as no energy at infinity. And you know that when you climb downstairs, you must lose energy. So therefore, it can only be negative in value. Right? Of course, we could have always done it the other way around and put the Earth as 0, or the center of the coordinate system as 0, but you get a very complicated expression. So that's why you put infinity as 0. And then you always lose. So that's why energy is always negative.
You always lose.
Okay? As a result, potential will also always be negative. Right? And the second reason, in order to get the negative sign, is due to the fact that it's an attractive force. Right? Because energy is defined as work done by an external agent. So if you keep losing energy as you as you come nearer and nearer and nearer to the origin, then the work done by the force to come nearer to the origin is positive work done. So the work done by the agent is negative work done. Okay, so this partially explains why it's a negative sign here. But the most important reason for energy is it starts at 0 in infinity and decreases as you get nearer and nearer to the object. Okay, and if you substitute in values of r, you will see why it is so. Like when r is very small, we are very near the center of we are very near the object itself. You should have very, very negative energy because you have to have lost a lot of energy to come to that point from infinity, which is 0. And if r is a very, very large number, you see that it's a very small negative number. That means you're actually closer away to infinity. Okay? It's quite amazing that we're casually tossing around infinities, right? Like it's nothing, like it's a particular point in space like that. Okay? Get used to it. You're math people. You'll do a lot more of this if you do a math course in university.
Even.
Yeah, you'll have like things like finite infinities and I don't know lah. My math friends talked to me about it before. Like there are different types of infinities even. Something to do with hotel rooms and number of guests and.
Oh, I know that one. The one where you have an infinite number of hotel rooms and infinite number of guests. Then technically, if you times 2, the hotel will full, but you can because.
No, but there's something like I remove all the even number of hotel rooms.
It's part of the bomb, so you slowly go down the chain and then go insane.
But it still looks like infinity to me. So my math friend was telling me that actually there's two types of infinities or something like that. It's quite fun. Okay, so this concludes the conceptual discussion. So let's go into the specific subtopics.
Satellite versus binary.
Yeah, okay, so these are a couple of things that I went through in the lecture as examples which A-level has you on. One is satellite motion. So satellite motion isn't specifically talking only about the satellites. Satellite motion is basically considering the case where you have one gigantic massive object, capital M, and a smaller mass orbiting it. Okay, so we call this satellite motion. It applies to actually any pair of masses as long as one is very, very large and one is very, very small in mass. Yeah, not size doesn't matter, but the mass. Okay, so that's called satellite motion. Okay, in a binary system, we go to the other extreme. The most extreme case of a satellite motion case is if this mass is very, very small and the orbiting mass becomes larger in mass until you end up with both of them being same mass. Then if they are same mass, then they have to orbit their center of mass. Right? Which means none of them is at the center. There's no object in the center. Right? So these are two extremes. And they are the rules that we can, or the formulas we can use for each one of them becomes different. So this is what satellite versus binary system is talking about, right? There's two different types of motion that we're talking about. The next big concept that I went through was Kepler's third law. Then after geostationary satellites and escape velocities. Any questions about these concepts that y'all had from lecture that y'all didn't understand or wanted to ask? No? Can I ask y'all? Since when in physics we ever learned the third law without learning the first two laws?
Because the first two laws are too difficult.
Because the first two laws.
That's why they put in uni.
First two laws are not because the third law is derived from other gravitational laws. The first two laws are not. Or rather they are, but like.
No, actually it's not that it is. The third law can be derived from gravitation, which is what you all learn in syllabus, right? For third law, basically what you're saying is centripetal force equal gravitational force. Then you do a substitution to find T squared proportional to R cubed. But I'd like to tell you the history of the third law. Kepler's laws are not physics laws. They're observational laws. So you don't need any physics knowledge, right, to derive Kepler's three laws. You need lots of data tables.
That's why they named a telescope.
Pardon?
That's why they named a telescope.
But it's actually very amazing, right? So he couldn't have done his work without the ancestors, all the astronomers that came before him, meticulously recording down the positions of the planets that they observed in the sky for a long period of time. So what he did to get Kepler's first, second, third law, okay, so in Kepler's third law, period proportional to R cubed. So he sort of had to know what the R is already. Okay, but what he did is he basically compared tables. So he looked at all the periods and then he looked at all the radiuses, and then one fine day he decided that why don't I just square the periods and cube the radiuses, and then aha, they're the same. There's a proportionality constant. Okay, but this is literally what we call an empirical law. That means he doesn't actually explain why the law works. It only describes that the law describes a set of data. And the set of data that he described was planetary data for the visible planets. Your Mercury, Venus, Mars, Jupiter, Saturn, the visible planets in the night sky. So you don't have Uranus, Neptune, and Pluto. And in fact, Uranus, Neptune, and Pluto don't follow this because their gravitational forces are subjected. In fact, Pluto's orbit crosses into Neptune's orbit. Yeah, now it isn't a planet, but still by right it should follow this law, right? Because this law doesn't necessarily apply to planet, it just applies to our solar system by right. Yeah, so it's not because Pluto is not a planet, but rather because in the outer solar system the gravitational forces are not so simple, right? Whereas in the inner solar system it's more simple. Hey Salat, how you feeling? You survived mosquito.
Hey, you collect the econ money, I give you money.
All the rest. I'm recording the lesson now. What? Yeah, dengue fever is no joke, man. I tell you, it can kill, even in the modern age.
I wrote the name.
But no side effect, right?
Yeah, got side effect. It feels very horrible.
I mean after cure.
Much like most illnesses, you do fail.
Okay, Cohen, good luck.
Thank you, everyone.
Okay, so where was I? So Kepler's first law, right, basically says that the solar system of planets are not in a circular motion, they are in elliptical motion. And the sun is at one of the focus of the ellipse. So this one I'm not very knowledgeable because I'm not a very math person. But the ellipse has two centers and they're called focus. So what he observed is if we model the planets as moving in the ellipse, then the sun is at one of the focus. So that's first law. Second law, as the planets move around the sun, they speed up and slow down. But they speed up and slow down according to a particular rule. In the same amount of time, they will sweep out equal areas. So you can see that here the radius is longer to the focus. So the area it has to sweep out will have to be the same, so it can only travel a smaller distance. Which means here, it has to slow down. And at this side of the orbit, when it's nearer the sun, because the radius is actually smaller instead of larger,
Circular motion.
so he must cover a bigger segment of the ellipse in order to sweep out the same area in the same amount of time. So this means when it's near the sun, it speeds up. Which explains why, right, comets take a very long time to go around the sun. Because comets' orbits are very highly elliptical. So you all know what comets are? Have you all seen a comet before?
No.
A comet is I haven't. You have? Where? There's a comet now, it's comet Neowise. If you look at Instagram, you can see lots of people photographing this comet. I mean, it's not a shooting star. The comet appears stationary in the sky. So it's a ball of dust, right, that produces a big plume that is very large in the sky, but it's not very bright. I mean, it's very bright for ancient times because they don't have technology. But in Singapore sky, you won't see it, even if it was there in the middle of the sky. It's very large. It can stretch to the size of a mountain or bigger, right? So basically what we are seeing here, right, is a dust ball or a snowball. But by snow, I mean volatile compounds, but not real snow. Okay, and the sun's pressure from the rays of the sun alone is vaporizing some of it. So that's why it leaves behind a pretty tail. So the tail is not necessarily the direction of motion. When it's moving towards the sun, the tail points away. But when it's moving away from the sun, the tail still points away. Because it's the sun that pushes the material away. So for comets, right, we can see them for a very short duration of time because during this segment, they are very, 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 very fast. Then they can take from tens to thousands of years to move in the other part of the elliptical motion. And of course, when they are far away from the sun, the tail disappears. So we only see the nucleus. Yeah, then it comes back again. So like there are very many famous comets, like one of them is Comet Shoemaker.
What about harm?
What?
The one that was supposed to take off like 5 years ago.
No, but comets, if he does, never mind one. Comets are snowballs only. It's asteroids that he does that has something.
that
Okay,
one
asteroids
called-
don't do this.
Was that one called Hamlet?
Called what?
Hamlet.
Hamlet? I don't think so. That sounds like a play by Shakespeare, right? So anyway, Kepler's third law, right, basically tells you t squared is proportional to r cubed, and this would have worked for elliptical motion as well, which the planets are moving in. So planet's motion is quite circular, like it's an ellipse, but it's a very circular ellipse. So that's why it's okay. Right? Now, Kepler's third law assumes this, and in our derivation of this, we have a few steps. Number one, we will say centripetal force is mr omega squared. This is where we get the period. In gravitational force, right, we will have gm over r squared.
Oh, mothers.
And because I can, no need the sign if it's a vector lah, huh? So I can always bring this r to the other side to get my r cubed out. And that's how you get t squared proportional to r cubed. Right? This only works for the satellite motion case. Why? Here, in the binary star case, let's assume that they are the same mass binary star as the extreme case. What is the distance between the two stars? Same, let's call this r. So the distance between the two stars is 2r. Right? So, in the gravitational force, this wouldn't be r squared, it will be 2r squared. Right? But the circular motion force, mr omega squared, this r doesn't care about the distance between the two objects. This one only cares about the distance between the object and the center of motion, or which is the center of mass. Right? So this one is actually r. So this one can't combine nicely to give you your r cubed. I mean, in this special case it can because it's 2r squared. But in the general case where one orbits at r and the other orbits at a different value of r, then you end up having a complicated expression like this, which does not reduce to t squared proportional to r cubed. Right? So this only applies for satellite motion. That's because your radius of orbit is the same as the distance that you use for gravitational force on both sides of the equation. The r's are the same. Okay, so that's Kepler's third law, something to take note about. It wasn't very obvious in the lecture when you study the material. Okay. Okay, okay about these two?
Yes.
Okay, then let's do question 1. So sorry, question 1 I already give you a more convoluted question than something that simply uses gravitational force, but you're still going to need to use it. So what we have is a SOHO satellite. This is a particular satellite that's trying to observe the sun. It's a helioscopic observatory. Right? Now, how many objects are there in this question? 3. Typically, your gravitation question has 2 objects. Right? So this already is a special case, you can tell. So we have the Earth. The Earth goes around the sun. And if we apply satellite motion to the Earth and Kepler's third law, we will know that if I know the distance from the Earth to the sun, we should be able to guess the period. And the question tells you, right, there's a satellite somewhere here. And the satellite is of course closer to the sun than the Earth is in the diagram. So if I apply satellite motion in this question again, right, this satellite can't possibly have the same period as the Earth. Right? Because it's closer to the sun. Then the question's premise can't be fulfilled, right? Because the question's premise is that this satellite and this Earth, right, must move in a single straight line as it sweeps around the sun, basically same angular velocity. So this satellite is not in satellite motion. Okay? In reality, right, where this satellite is, right, is very, very, very near the Earth. It's not that far from the Earth, but I need to exaggerate the diagram, otherwise it's very hard to see. Right? So this distance in my diagram is small r, and this distance is capital R. So we can still do free body diagram for the object. This is my satellite. What are the forces acting on the satellite?
Only gravitation.
But which one though?
Earth. Earth is shorter, Sun is much.
Why must the sun's gravitation be larger than the Earth?
The Sun is much heavier.
But I can always move my satellite nearer the Earth to make the Earth's gravitational force larger, and it can balance. Why must the sun's force be larger? So the answer that the sun is more massive is not correct. As in, it's true, but it is not relevant to the answer. Why must the sun's force be larger than the Earth's force?
Because moving on the sun.
In?
Circular motion.
That's right. I'm moving in circular motion. So in order to move in circular motion, I need a net force pointing towards the center of the circle, which is the sun. Right? So therefore, I need to have a net force in this direction, so that I have centripetal force. In fact, if this were a long question, that should be the first statement to say. The net gravitational force provides the centripetal force.
No, we need this for every single question.
That's to do with circular motion. Right? See, so once you make this statement, right, the equation comes out naturally, right? Net gravitational force is literally force due to the sun minus force due to the earth. That gives you your net force. That's this one. Provide centripetal force equal centripetal force. If you look at the options given to you, right, they are all mr omega square type expressions. So centripetal force, we're going to use mr omega square. Which r should I use for this motion?
Capital R.
I should use capital R, right? Because this is that distance to the center of the circle. So it's capital R omega square, not small r. This one eliminates one of the options already. So for the sun, it is gmm over r squared, and it's capital R squared. For the earth, the distance is small r, so it's gmm over small r squared. And of course, the capital M's are different because they're provided by the different masses. So this is mass of the sun, and this is mass of the earth. And small m is the mass of the satellite. So which option should this answer give be?
What about the minus sign?
So normally the minus sign for force, right, is a vector sign, right? It tells you the direction, given the sign convention is to point away. But now I'm just taking my free body diagram as this direction is the direction that the force points in already. So I can ignore the minus sign in this case because I'm only using its magnitude. Right? This magnitude minus this magnitude gives me the net force in this direction. So the minus sign is only useful when you say, oh, I put my sun in the center and I need to draw graphs and all that. But it's not so useful when I'm doing subtraction, doing free body diagram, because I already have defined where the directions are. So you can just use magnitude minus magnitude. So this is the same as like in dynamics and forces, right? We don't always care so much about the minus sign in forces because we already draw the diagram to see where the forces are pointing. Right? So we didn't use the minus sign, but rather we used the magnitude. So what's the answer? Is it D? D, right? So something very interesting about these points, right? These points are not your typical satellite motion about the sun points, right? Because they are not free. They move in a special period. The period is related to the period of the Earth as well. We want them to move at the same period that the Earth is moving. So it's because I can use two forces and make them subtract enough so that I slow down the satellite. Sorry, this will be satellite. Slow down the satellite so that it can match the same orbital period as the Earth. So we call these special points Lagrange points. Okay, your math fans should know the word very well. Lagrange is a mathematician, right?
Oh, we haven't known.
Yes, it's no smiling. He loves Lagrange.
What's his famous law?
I don't know. I'm not mathematics fan. So know what's his famous law? Mean my what? Okay, no, know that. Do I know that? Am I supposed to know that? Is it a physics thing? All right. Cocktaility. Is it like how nice the drink is? So he's a very important mathematician, right? Yeah. So the Lagrange points are named after him. Huh? There are many Lagrange points, L1 to L5. So I can't remember which one this one is, but basically if this is the Earth and this one is the Sun, right? There's a point here, there's a point here, there's a point here, there's a point here.
It's L1.
Really?
You put it.
So I wrote that, this is L1. So Lagrange points are points that they will appear to move together with the Earth as the Earth moves in the orbit because of the special combination of the force. So first for these points, right, it is because of the the diagonal components that gives it a centripetal force that we just nice again. Right? And they move around with the Earth. So these are actually very great places, right, for us to put our first people who live permanently in space, basically our space colonies. Yeah, if you watch any anime or Gundam, right, it always involves space colonies, and they always put the space colonies at Lagrange Points. Yeah, then the people of Earth always get jealous of the people in space, so they either surprise them, which leads them to revolt against the Earth, or they nuke them, which gets them to revolt against the Earth. Right, so yeah. And then of course the climatic apocalypse in all these stories is people who are in space are unhappy with the Earth, so they drop a colony on the Earth.
So they all the weirdos are gone.
But yeah, I know, right? Sad. Inzu would have been like, and Eugene would have been like,
Eugene was just this.
So anyway, that's the idea lah. These are Lagrange points, but it's good to put. I think we do put some satellites in this position. There are some very obvious benefits. Like for example, the SOHO is able to constantly observe the sun because it doesn't have to go around the Earth. You see, it's orbiting the sun, so it doesn't go behind the Earth, which means it never ever loses sight of the sun. Right? It never gets eclipsed. It continually able to get data, and furthermore, right, it's able to constantly communicate with Earth. Right, a satellite that's moving around the sun may have to go opposite side of the sun while the Earth is still on this side, because it has to orbit faster. Right, they have different periods. Just like Mercury and Venus can end up with on the opposite side of the solar system. Right, so this satellite is always in line with the Earth. There is some disadvantage though. So if it's trying to observe the sun, the part of the sun it's trying to observe may rotate to the other side, but it doesn't follow the sun. It's not in geohelium. It's not in heliostationary orbit. Yeah, that's the correct word. Right? So it can't observe the same part of the sun continuously. Similarly, if it's actually in communication with a particular base on Earth, the base will rotate away to the other side at the night time. Then you can't communicate with the base without the use of other satellites to bounce the information around the Earth. Right? So there's a disadvantage of putting it in this Lagrange point.
Do we put ISS there?
Do we put what?
ISS.
ISS? No, ISS is in a low Earth orbit. So that is, I think, easier to get to the ISS. Yeah. So this is considered a high orbit. It's a far away orbit. It's not very near.
What are those low Earth orbit do?
They orbit the Earth much faster, lor.
What can they do?
What can they do? They're just all different orbits. So satellites orbit at different heights depending on the needs of the satellite. Like for example, if it's a camera or sensor, sometimes the resolution is limited by distance. Right? So you want them to be placed closer. But the bad thing is, if it's placed too close, it will orbit too fast. So the solution is you put many, and that's what Starlink satellite is, right? Our Elon Musk one. Okay, pretty fun discussion for question 1. Okay, any questions? Okay, let's do 2. Then we can call it a day for physics.
2 questions.
Yeah, but I did the summary as well. Huh? So this part is more algebra work, which you all would probably like. Express gravitational field strength in terms of rho and r. So traditionally, our gravitational field strength is G capital M over r square, right? So the capital M is not allowed in this question. So we can replace the capital M with density is mass over volume. So mass is density times volume. Right? Sorry, did I indicate a cube accidentally? Then volume of a sphere is 4/3 pi r cubed. So we get G rho 4/3 pi r cubed over r squared, which reduces to G rho 4/3 pi r. So let's neaten it a bit. I can bring the 4/3 in front. And the pi can put behind the G. Then rho. Then the only variable is r.
Wouldn't you put pi in front of G?
But G is also constant. The 3 of them are all constant. G rho pi, pi rho G. Right? Yep. No need. Right, because I never specify any coordinate system. Okay, so that's the magnitude of the G field strength. If you want to, it's okay, no problem. Yeah, you just end up with minus 4/3 pi G rho R. Okay? Like, you okay, this one? You all managed to get it? Anyone not very sure how to do this kind of algebra? Basic stuff, right? Okay, part B then. The question says that now we want to consider what's the same G, right, for an object which is 3 times denser but half the radius. So now we have G2 of the second object. It's 4/3 G pi rho, but the rho has changed now, so the rho is a variable. That's why I put the rho behind, right? The rho for the new object is a different rho. So before I do any manipulation, the trick to do it is give it the appropriate subscript. Then later do the substitution, then I won't forget. So this is rho 2. G remains the same, pi remains the same, so no problem there. The radius also changes, so I'll call it R2. Then I'll do my substitution. Rho 2 is 3 times O rho. R2 is half of OR. OR. R is half of OR, yeah. Then I can pull out the 3.5 to get a 1.5 here. Then I'll end up with 4/3 pi rho GR, which is the same expression as before. So that's just G. So this is G2 in terms of G1. So it's 1.5 G. Right? Okay, looks like a good place to stop for question 2. Question 3 at the start, there's some definition-based questions. So let's clear A, part 1 and part 2(1) also, okay? Center of mass. Anyone wants to explain what center of mass is? It's like difficult but not. It is not necessarily the geometrical center of a body. Yeah, it's just an imaginary point or just a point where the mass of the system appears to act from. So how do we determine it? All you need to do is just keep moving further and further away. Then the two mass, the point where the mass act from will be closer and closer to the CG. It will seem that it's the CG. Right? So that's how we determine where center of mass is. Of course, you can just do a weighted calculation to get it. Right? It's not the geometrical center. It is only the geometrical center for regular objects. But for example, the moon, right, is not a regular distributed object. The moon is denser. The moon is denser on the side that is facing us. You all know that the moon always gives us the same face, right? That's why we always see the rabbit and the... What other animals are we supposed to see there? The woman and...
The tree.
The tree, yes. Chang'e, right? Yeah, so we're always seeing the same face. That's because the moon is tidally locked to the earth. There's something called tidal resonance in astronomy. When two objects orbit each other too closely, right, over time, right, they will slow their rotation down to match. So that the earth rotates and the moon will orbit at the same rate at which the earth rotates. So therefore it always is turning just nice so that the same face faces us. Yeah, we call this tidal locking. Very interesting, right? Now, the moon, right, is not uniformly dense as well, because the moon's dark areas are actually, the moon is actually punctured by asteroids in its early life, right? And its inside, when it was in its early life, the inside was still magma, it was still liquid. So the dark areas you see on the moon, the maria, the lunar maria, okay, that's the dark areas on the moon. They are actually made of higher density material than the white crust. Yeah. So, pardon? Well, what would that be that you want there? That you can't get on Earth? That you can't take from poor countries?
See, the poor countries won't be around for much longer because Greenland is melting.
And it's melting, then there'll be more areas to mine.
No, but see, Greenland is melting. But that also means that like a lot of poor countries are about to not exist.
You mean to be underwater, like Indonesia and us? Moral of the story, don't invest in Singapore properties, right?
Isn't it better than first?
Yeah, I suppose so. And Venice. Yeah, anyway, the moon's material is largely similar to the Earth's crust. So that's why the lunar impactor theory is the leading theory on what produced the moon. Right, there was some object that crashed into the Earth in its early history, throwing up debris that orbit around the Earth until it coalesced into the Moon. So anyway, the Moon is not, I think if I'm not wrong, part of the Moon is denser in our side than in the opposite side. Okay, so it's not uniformly dense. So its CG is actually not exactly in the geometric center of the Moon. Yeah, but most objects are spherically distributed. Like the Earth, even though the center is denser and the crust are less dense, it is still geometrical center because the density distribution is in a radial direction, and the Sun as well. Yeah, but for irregular objects like my water bottle, the geometric center is here, but the center of mass is not, right? Yeah, because my cap is made of plastic, is much lighter. So same for this as well. Like if I leave it like this, most of the fluid accumulates here. So although this is the geometric center, the CG lies below it. Okay? Right, so that's center of mass. And then the second one is just bookwork, right? Gravitational field strength